Here we are going to solve a very interesting geometric optics problem from site brilliant.org, and it was posted by Mr. Brian Charlsworth of Canada. It's a very interesting collection of problems on that site, and especially the ones that Brian has, so I'll urge you to look it up. Well, the problem goes something like this, and I'll sketch as I say. There is a square over here, and at two corners of the square there are two circular reflectors, and they are of unit radius. So these are the two reflectors, and then a ray of light comes from the corner between these two and strikes the first circle, gets reflected, strikes the second circle, gets reflected, and returns exactly back to the corner here. And this triangular path happens to be an equilateral triangle, provided we have the length of the square right. So what is that length? What is the length of the side of the square? So let us start solving this problem by first plotting a corner A at any arbitrary point in this plane, and then I can draw these two sides at right angles. I don't know their length, so just unknown lengths here. And then we can also show this equilateral triangle. We don't know the size of this triangle. We don't know how big it is. But we know it has a vertex at A. So we know its location, number one. We know its shape, it's equilateral. And we can also know its orientation, because from the problem statement, we can rest assured that this triangle will be symmetrically located between these two sides. So this angle is 60. So the remaining angle 30 degrees will be split into two halves, and therefore it will be making an angle of 15 degrees with both these sides. Let me zoom in here so you can see it better. Then we can also draw the normal, or at least the direction of the normal, not the location, but the direction of the normal. See, this is the incident ray, and this is the reflected ray from the first circular reflector somewhere on this line. But these two are going to make equal angles with the normal. So the normal is going to be the angle bisector over here. So let's show that. Okay, we don't know the location, I'll repeat, but we know the orientation of this now. Then I'm going to just draw an extension of this line, and on that I will draw that circle of unit radius over here. The center of this circle will be at an elevation of 1 unit, and I'm going to copy this normal over here. See, the normal is a normal to the circle, and normal to a circle is nothing but the radius. So this line, or a line of this inclination, must come from this center like that. Let us just chop off this extra length. So this is how it's going to look. The circle center is going to be at elevation 1, and then there will be a normal drawn up to this point. So this will help us figure out the elevation or the y coordinate of the point of incidence. So let us take that point of incidence, or I can actually take this whole circle and I can move it over here. Okay, and we can find this elevation now. This elevation is going to be this 1 unit plus the height of this small triangle. Let me zoom into that area so you'll see it better. The angle here is going to be 15 degrees. This is hypotenuse is 1. So this height here is going to be sine of 15 degrees. Let me mark that distance. So this is 1 plus sine of 15. Now we can draw a triangle like this, whose height we just figured out, whose opposite angle we also know, and it being a right angle triangle, we can now figure out its base. So that is going to be equal to this height divided by tan of 15 degrees. So we have figured out the distance from here up to the point of incidence along the side of this square. Next, we can take this part of the triangle, or the base of this triangle, which is going to be 1 into cos of 15. So let me mark that 15 degrees and that cos 15, plus we will have this much of distance, which is nothing but the radius. So let's mark that as 1 unit. So the length of this side is going to be made up of these three parts: the base of this triangle over here, plus the base of this little triangle, plus the radius of the circle. So our answer is 1 plus cos 15 plus 1 plus sine 15 upon tan 15. That's going to be the dimension of the square. So let's draw the rest of the diagram. So my sincere thanks again to Mr. Brian Charlsworth and Brilliant.org.